and then we'll get all the others. So all this is doing absorption. It's just showing you how we're sort of one step here to create a gradient that everything else will follow. You don't
Sodium's kind of like a little catalyst.
Yeah, because that's what we use the sodium potassium pump for, right? Because that's our big guy that we use in every cell. So we'll use that with ATP to pump sodium in this direction, and that creates all these gradients that it's almost like dominoes falling. But all this is reabsorption. So.
Okay, so nothing ever gets, once it's reabsorbed, it doesn't get...
I won't say that, but that's chapter 1. We're going to talk about secretion and of things from the blood going into the lumen.
Okay, so I think that's what's confusing me, that we've only, like, you kind of explained half of it. Because by half, it should make sense that it would go the other direction.
Well, but most of them, no, I mean 99%. See, we put so much in, 99% of what we put in is going right back. Okay?
Okay.
So, I mean, that's sort of the idea, which is a little weird when you first think about it, because it seems such a waste of time. But really, that's why it's bulk absorption. We get everything in, 90% goes back, and the rest of the way, we're going to do that fine tuning, which is sort of the beauty of the kidney. So most of it in, back. Okay? It's just that we don't want to waste time on the going in to do, okay, we need this transporter. We want just like everything that cells and protein gets in, we'll take most of it back, and the rest of the way we'll fine tune and help us live.
Okay.
Which is chapter 1.
So the sodium potassium pumps out all the potassium. Or yeah.
Well, all we're talking now is the sodium at the moment. Yeah.
So sodium, and then because it's a coupled reaction,
It's not really. Well,
moves the secondary.
oh, for that?
Yes. To move the to glucose.
Yeah. It's let me get to the actual final picture too. So it is a coupled reaction and different than I might have said it before, but they are all coupled together. We skipped chapter 5, in which it's actually a test question on this, but we didn't do that part of it, and that's what you would have seen it the first time, but I was sitting there. But yeah, you have this idea. This is sort of the first step. And that's why the way they number things are always wrong in the book. That's not third. If this didn't happen, nothing would happen. So don't worry about potassium now. We look at the sodium. By pumping sodium out, that means inside the cell, very low sodium compared to out. That means we've got a concentration gradient, right? We put water in a dam. That's potential energy, right? Everyone see that? Low in here, but now we have high outside. Because which way does it want to go? High to low. So if you have high out here, okay, we need proteins because ions can't just cross, or things like glucose. So the idea is, if you have a transport protein here, it naturally will go from high to low now. It wouldn't have done that if we didn't do this. So this is, again, it's like putting water on the dam. If you open it up, water's going to flow down, right? You put it up there. But we don't just use that, right? We use it to make electricity and drive something. That energy we created here, and as it goes down, is driving glucose to go against its concentration gradient. Glucose, which would be hard to get all of it out, right? Well, basically, it's going to piggyback on that in a way and use that energy to get all of it out. It couldn't do it on its own because you can't go from low to high without energy, right? Anytime you're going against the concentration gradient, you need energy. But instead of using ATP directly, we call this secondary active transport. Active transport is needing energy, right? This is primary because you use ATP. This sets up the gradient, and now this transport protein will basically...
So the glucose just hops on the sodium?
Well, it's a transport protein. So it has a slot for... Yeah, they both like bind in different spots. The thing is, because sodium is binding so fast, it's sort of facilitating the other one to come on. And that's the piggyback. So it's not the same part of the protein. We're just showing it like a ball here, right? But it's a protein with sites for glucose and sodium. But the thing is, what's going to happen is because sodium basically is so abundant, it binds, makes the site for glucose, it comes on and gets in. And we can get all of it out then, that you couldn't normally get. What that?
What is it?
It's, what do you mean, what is it? Yeah, well, it's called the glucose, it's called the glue transporter, right?
Okay.
The thing is,
So it's something physical that they both kind of attach to.
so it's one protein that they both attach to. Again, chapter 5 has pictures of it. We skipped chapter 5 because we ran out of time. But you can go back to that, so even the notes I have on it, you'll see physically what it looks like. But yeah, it's a physical protein with binding places for sodium and glucose. And then, basically, they both bind, and once they bind, it ships it, and they go to the other side. So it's literally proteins which are transporting something from one side to the other.
And they do this for what? Again, I know that sounds like a really dumb question.
All this is to get all the glucose reabsorbed. Because we don't want it in the urine, okay? It took a lot of money to buy that candy bar, and we don't want it to go in the urine, right? We want 100% reabsorption of the amino acids and glucose. So we set this up with this, and then whether it's either it's the amino acid sodium or it's the glucose sodium guy here, basically that energy is used to suck all the glucose back, and then all the amino acids back and reabsorb it right there. So unlike ions, which kind of can go through pores and stuff, we need physical transport proteins to do that. We sort of do it sort of in this way.
Okay, so that's for all the cells and proteins that couldn't get through in the
No,
first place.
cells and proteins are out here.
Oh, separate.
This
That's
is
separate and apart.
see that's why I know I talk about it. The proteins are these carrier proteins. These are just in the membranes.
Okay.
Their job is just to carry things from one side to the other. They're just part of it. They're not the proteins out sprayed by the liver. They're out here. Cells and proteins don't make it in. We're talking salts and glucose, etc., make it in. We've already talked that all the salt stuff get reabsorbed by the way we just said, but the glucose and amino acids need this specialized transport method here. Again, details of this, don't worry about it all, because we're not going to cover it on a test per se. I'm not going to make you do these steps on the test. We haven't enough of it. So really, I wanted to show it, but really the idea is literally what I just said. What you want to remember.
Glucose to be reabsorbed.
Yes. Really, all of this, even though it's too complicated, really all of it summarized is in proximal tubule, bulk reabsorption, most of the salt, most of the water, all the glucose, all the amino acids. That's what you really have to know about that. That's it. So some of the detailed mechanisms, don't even worry about. You really just have to know that, because the detail is coming. Chapter 20 is awaiting, okay? And you'll get more detail than you can believe. Chapter 20 is the hardest chapter of the course. But it's the most fun. I promise you. Oh, it's so cool. But you got to get all this. Try to get all this you can before you hit chapter 20 a week from today. Okay, because we have a holiday. That holiday messes us up. Okay, if you're going to give us holidays, let us off December 6th. Put all the holidays at the end, right? Instead of making us go to the 16th. This holiday is sort of. I know you can't do that, but it's disruptive. When it comes down to it. I mean, holidays are great, but they really disrupt the schedule. And I wanted, again, the key with this is I had a choice. Either we don't cover it all now and you have to study it over Thanksgiving, or we get this done before Thanksgiving. And I'm like, we want to get this done before Thanksgiving. Okay, this is nuts, okay? You want to think nothing in Thanksgiving. So, but don't forget, by the way, even if you're leaving, if you haven't picked this up, make sure you pick that up as well.
That's Wednesday, right?
Yeah. And those are respiratory problems and blood type problems, and anything else in the lab you'll see. You should be okay on those.
So when you're talking about agglutinates, it's when it pumps?
Yes.
A question about the factors respiratory properties. Specifically, number 3, I don't even know what the last option is really asking.
We might not have had it yet. I don't remember.
I think we have gone over this. I just I'm having trouble understanding that. The very, very, very last.
Oh,
D.
that's a hard one. Okay.
I guess I understand what the other options are saying. I just don't know what that last one is saying. Yeah. What the
What do you mean? What don't you understand?
I guess that's what it's mean and its role in this.
Oh, well, you need to look at the slide and what we went on as far as when we talked about what controls bronchoconstriction and bronchodilation. Do you remember that? Because, really, to answer that problem, you have to remember the whole thing. We have this, you have it on your notes and everything too, but we had bronchoconstriction. That question, which some people might not want to do yet, you don't want to necessarily do it unless you're there. Let's kind of just review that. Bronchodilation.
Super, we went over this.
But we went over this, but that's one of the harder questions, by the way, because you're going to combine two things on that. You're combining the thing we did at the end of the chapter of how the pulmonary arterioles work opposite to the systemic, and you're combining what causes bronchoconstriction and bronchodilation. When we talked about bronchoconstriction, okay, what caused bronchoconstriction? there was parasympathetic. Okay, so this is, and people already got their notes. Parasympathetic, which again releases acetylcholine, and they bind to answer that question he's talking about, you need all this information and kind of do it. Acetylcholine bind to muscarinic receptors. The other thing that caused bronchoconstriction was histamine. That could be from allergic reactions. And that just binds the histamine receptors. So that question is involving antagonists and agonists, but you've got to remember that. For bronchodilation, what caused bronchodilation? Epinephrine. Remember, sympathetic, norepi is not involved in this, but those are involved. So you have to know all that to answer that question. Okay, what it causes, bronchodilation, bronchoconstriction, and remember these things as well, because epinephrine, oh yeah, one more factoid there. What does epinephrine bind to? Beta 2. So if I'm doing beta 2 agonist, antagonist, you got to realize that. So you need that information in front of you. And then you need to remember the idea of what we did at the end of chapter 17, which is, what does the pulmonary arterioles respond to constrict and dilate versus the others, right? And so for that one, we can kind of do it again, just to set you up. I'm not necessarily answering that question right now, because I want you to think about it and start going in. So this is, the end of chapter 17, which, that's, since we're doing this, again, here I'm pretty much doing whatever people want, and
And you said it matters bronchoconstriction, dilation, and pulmonary arteries?
where I'm doing, I'll tell you right now what I'm doing. To answer that question, you've got to, I guess I'll go up. And I'm going to review how I did it again. You've got to remember that as far as these gases go, oxygen and CO2, that the pulmonary arterioles, what they're doing is opposite to the bronchioles and systemic. That was like the weird or the harder concept in chapter 17. You need all this information to answer that question. And just to remind us then, because that's what these review sessions or wherever are for, are some of the harder things. Not the perfect picture, but we are going to show this over there.
The bronchioles.
Say that one.
The pulmonary arterioles are being the opposite of the bronchioles.
And opposite of the systemic arterioles as well, which is, again, part of this. So I'm just redoing it like I did before. We have the systemic arterioles. We have, these represent the blood vessels. These are the pulmonary arterioles. God, this board is so. And here are the bronchioles, right? The control into the alveoli. Which, again, we're looking at the chart. Are you seeing how I'm organizing it here? And then we're not looking at all the gases. The bronchioles, the pulmonary arterioles, which is hard to visualize by that, are shown here. The pulmonary arterioles, they're flying by the alveoli to pick up oxygen, right? And there's like 1 billion of these alveoli, or maybe that's too many, but 100 million or something like that. And that's what these represent, these pulmonary arterioles here. Going by, these are the alveoli, or 2 of them. Okay? Now, just to remind us of how we sort of described this effect, okay, of being different. Okay, I did it in the form of sort of, the jobs that they have. Again, common sense. And so the systemic arterioles, again, we're looking at gases. And basically, I made the example of low O2. Let's say, and how these things are going to respond to low oxygen. And remember, the one in the middle is going to respond differently, and we want to figure out why, because that's always opposite. And remember, by the way, for that question helps too. If I'm saying low O2, that also means what? High CO2. So if I'm saying high CO2, it's like low O2. Again, you just almost even write it next to each other, because who knows what the question is going to say. But the idea of that low O2 is if these systemic arterioles are delivering oxygen to tissues and you have low O2, what are they going to do in response to low oxygen? Dilate. Their job is what? To deliver more oxygen. Systemic arterioles, which is what we did before. It was called active hyperemia, right? That if you had low oxygen here, that since this is carrying oxygen, its job is to deliver oxygen. Deliver O2 to tissues as it needs it. So that if you have low oxygen in the tissue, it has it, it's going to vasodilate. And that will help us deliver oxygen. And, by the way, get rid of CO2 as well, right? We're going to increase flow here. That was called active hyperemia. Does that make sense? That's why the systemic do it. Again, I like just the idea of delivery. It delivers oxygen. You go to the other side, because remember, the other side is going to work the same way. You go to the bronchioles. The bronchioles, constriction dilation, they're controlling oxygen flow into the alveoli and therefore the rest of the body. If the bronchioles say, look at this, and look at the, or examine the oxygen levels, whatever, are responding, and it's low O2 in the bronchioles, what are they going to do? Dilate. Because their job is what? Deliver oxygen into the alveoli. So this case, the same way as the out one. They're going to, again, their job is to deliver, from the atmosphere, deliver O2 to the alveoli as needed. Therefore, under conditions of low oxygen, they're going to bronchodilate.
The systemic arterioles, was that one of the local controls too?
That was one of the two local controls that we did last time. This was, again, called, where are we here? Active hyperemia. And the other one we talked about today, too. The myogenic autoregulation. Do you see how the course built upon it, right? This is not that new. It's a little new, some of the stuff, but it's really just, okay, we've had this before. We're just adding one more step to it. Now, here's the weird one. The pulmonary arterioles, exact opposite to those. And let's have it make some sense, and then we can use the word. Okay? We have 100 million or something, whatever. I keep changing the number. I gotta figure out that number. Of alveoli with different oxygen amounts. Okay? Now the idea of this is, and we're just going to look at the low oxygen one, and again we can show their picture here. It's kind of better. So these arterioles and capillaries, they're basically coming, from the right side of the heart with low oxygen. We want to pick up oxygen, and that's going to be the key why it's going to be different. The job of the pulmonary arterioles they're not being paid to deliver; they're being paid to pick up O2 from the lungs and deliver it to the left side of the heart so it can go to the body. They're passing through. They've got all these different alveoli. They've got to choose which ones to go to. And here we've got a choice here. Now we have two choices here. This one is the one we've been kind of playing with, right? Low O2. You've got a choice of going to this one with low oxygen or this one with higher oxygen. And you're getting paid for how much oxygen you pick up. That's your paycheck. So if you've got a choice, because you've got a lot of time, you can't go everywhere. If you've got a choice, are you going to go to this low one or this high one? So what are you going to do over here? Constrict. And then this one you'll dilate. And that's what happens. That's why it's opposite. And we'll show you the term up here as far as the official term of it. But basically that's why you're going to see it's opposite. The job, in my mind, making it sort of simple in my mind, I'm doing jobs, right? The job is, since it gets paid to pick up, it's going to go where the oxygen is. And so basically where it's not this time, it's not involved in sort of delivery. Or those other guys are doing it. Its job is pick up. It's like, okay, I'm not going there right now. Okay, I'm going to where the oxygen is so I can pick up the maximum amount of oxygen and pay my rent. Okay, it gets paid for pickup. The other one gets paid for delivery. It makes sense. There's not enough there. We'll open up and deliver. This gets paid for pickup. It's got so many to choose from that it chooses where there's more oxygen. That's why it's opposite. Low O2, constrict. The official term for those who really want sort of not jobs and not talk about, the job and all that, because that's obviously just a way to remember it, is the following. We're going to say that ventilation, which is how much oxygen gets in, matches perfusion, which is how much gets to the blood. So if not much oxygen gets in, not much is going to get to the blood, right? Less perfusion. If this one, a lot of oxygen got in, that's ventilation, that's going to increase perfusion, what it gets in the blood. It's a match, right? You don't get much in, you don't get much to the blood. You get a lot in, it goes to the blood. That's sort of the official terminology of it, of ventilation matching perfusion. what gets into a particular alveoli, how much oxygen, is going to match how much gets to the blood by this process.
Does it simultaneously constrict one and then dilate the other?
Yeah, because we're just passing through right away. So as it's passing all these local factors are kind of affecting these arterioles directly. So as soon as it gets near one of these, the oxygen, all those factors will cause it to constrict and dilate. It's just that it works completely opposite than it does on these outer ones.
Quick question, you said perfusion versus what?
Ventilation is how much oxygen got in, right? That's ventilation. And that's going to match perfusion, which is how much actually gets to the blood. That's what the definition of perfusion is. Going from here, the alveoli, into the blood. How much actually gets there. And it matches. More in, more perfused. Less in, less perfused.
Perfusion, how much goes into blood, actually goes into blood. Ventilation, how much actually goes into...
Ventilation is how much air, how much oxygen we got into the alveoli.
Into alveoli,
Right.
blood.
And that's going to match perfusion, which how much gets to the blood. And you can see that. Here we had low O2, not much got in. Well, not much is getting to the blood. You can drink it. A lot got in, it matches. And so that's, most people, the books aren't going to talk about jobs and pick up and delivery. But for my mind, it helps me to do that. It makes sense. But, hey, if you want to impress your friends with ventilation perfusion talk, go ahead and do that as well.
Yeah. Bronchoconstriction, vasoconstriction in the bronchioles, or is it?
No, it's bronchoconstriction. I mean, bronchoconstriction is literally what we set up here, the things that are controlling, besides local factors, that are controlling constriction and dilation of the bronchioles. So, that question you need to write out. I'm not going to tell you right now. I mean, the question he's talking about, your question is really putting all this information together in kind of a critical thinking one that's going to be on the test like that. But it's a really hard one. That's why I'm putting on extra questions. And so, again, to do that, you need all this information and then piece it together. I'm not going to go through that right now, though.
Right, yeah, I'm just asking to better understand.
But you want to know this is the tools you need.
Cool, thank you.
So you need a lot of it to answer that question.
All of it.
Yeah, you need all of it, but it's fun.
I was at a loss at carbon dioxide transport.
Well, which particular loss? Let me kind of get it up.
I understand the loading part, I guess, but the unloading is where I...
Well, we're not you talking about oxygen or CO2?
No, CO2.
We're saying it just reverses. We're not going through it all. Everything, what is this? We're only talking loading. All those 6 steps were how we loaded it from the tissues here. Then it's going to be the cardiovascular system will transport it to the lungs, and everything we did up there reverses. But I'm not going through the steps.
Oh, okay, because we want to get rid of some, so we need to load everything.
Yeah, so that's the idea. In other words, we're trying to maximize getting rid of the CO2. So all we can do is diffusion. That's how gases work. We kind of did that with oxygen a bit with the hemoglobin. Now we've got these other ways to do it as well. And so we're maximizing. Plus, that bicarbonate, which is really nice, is a major extracellular buffer. So while we're doing this on the way, that bicarbonate going through the plasma is also acting as the major extracellular buffer for any acid we got in. So we're just showing you how we basically get rid of the CO2, loaded from the tissue into the blood, so that when we make it to the lungs, we'll be able to get rid of it. And all of this in the lungs will have the exact opposite ways. You can almost make them 6 more steps. You don't want to do that. But it's the exact opposite. But do these 6 steps sort of make some sense?
Yeah, I just didn't know the overall holistic purpose, so
Right.
now I see. Yeah.
So yeah, you want to, because again, hypercapnia. You don't want to build up CO2 that starts acidifying things. So we're really pretty careful on doing that.
So it's to prevent hypercapnia,
Yeah.
the 6 steps?
The 6th step is to maximize getting rid of CO2 so that we don't develop hypercapnia, which is buildup of CO2. Because that related directly to acid and acidosis. So remember, even when you're thinking of 18, you've got 6 steps of oxygen transport. Easy, right? I mean, there's really nothing to it. I mean, compared to the rest of the stuff. That's the first thing. Then, the hemoglobin saturation curve and its friends. That's the hard one, okay?
The 5 other
The
guys.
the 5 shifts and how it works. But if you go through it step by step, I don't think it'll be as bad. Then you have the 6 or 7 steps, whatever you're going to call it, of this, right, which were just chloride chip steps, and then just the control. Peripheral receptors respond mainly to what? The peripheral chemoreceptors for ventilation.
Just on that.
What? Oxygen. The central ones, carbon dioxide. Boom. That's all. So the hard part of chapter 18 is really the hemoglobin saturation curve in front to do it. And you really, I mean, again, I could go over it again, but I mean, that's what you have to sort of play with. Start from scratch, you whiteboard, you draw it, what's happening here, what's happening here. What does the shift to the right mean? It's losing, it's less affinity and all that. What conditions would do it, and it should start to flow. And actually, it's really a hard thing. I mean, that's a hard thing. That's the hardest thing from 18.
And the CO2 transport control that you just said too.
Well,
we
I
get
guess.
that down, right?
Yeah, you have to.
Like by chapter 20.
So what's that again?
By chapter 20.
What about
like, we have to get the 6 steps of CO2 control, transport control, like definitely by next week or by Wednesday.
Yeah, you want to have everything we've done almost except, as much as chapter 19 that you can do as well. You want to get as much as you can, between this week. Go through everything almost as if you were taking the test and seeing what questions you have on 17, 18, and 19. Because this is literally 3 chapters we've done. So the most you can do of that, because in chapter 20 is like, you want your head almost clear for chapter 20. Chapter 20, you want to come in drinking some stuff, I don't care what it is. Or even looking ahead if you can. Chapter 20 is hard, and again, we're going to spend, 3-4 hours on it, but it's hard. So you've got to be prepared for that. If you're not doing all this, it's going to be not much fun. And then really all we have to do the following Monday is, review the extra questions. The hard part of them are, except for that one, hard part of them are on chapter 20. So that's why we have 2 shots at chapter 20. We have next week to get it, and then over the weekend and stuff, and then the following Monday to get it really well. But these first 3 you want to have down. Because you want your head, like, I kind of have that, I'm ready to restudy it, chapter 20. You want a free mind for chapter 20.
I wish they weren't together. That'd be kind of nice.
You wish what?
They weren't together. Like chapter 20 could be its own thing.
Yeah.
And then these guys could be their own thing.
Yeah.
That'd be really cool.
They can't be. Sort of thing.
What was the bulk of chapter 18 that you said was?
Well, there's 4 things, right? There's this, and really the hard part is the hemoglobin saturation. There's the 6 steps of oxygen transport, which I sort of simplified, right? We wrote down. That's not too bad. Then there's the hemoglobin saturation curve and shifts.
Yes.
That's the hard one.
The
The Diablo and friends. And then there's this, which is sort of simplified as far as the 6 steps. And then there's just the peripheral and central chemoreceptors respond to oxygen. I mean, that's all that you have to know from that. Sir. BP.
Now, do we have that normally and it adds on to bring it to the right?
Yeah.
And we don't have it, it goes to the left?
If we have less of it, everything, there's nothing absolute, right? I mean, you kind of get that. I mean, so we always have some of everything. Some of these hormones, some of, so right. We have because we have a normal amount of 2,3 DPG. So we either increase it or we go less than normal. And if you're hypoxic and you're performing more glycolysis, or actually just if you're, let's say you're a sprinter and stuff and you're doing all that as well, you're going to be having more 2,3 DPG, shifting to the right, and your hemoglobin will release more oxygen, which of course is a good thing. So yeah, everything is in the middle, basically.
And the bulk of what we just did for the kidney was the filtration and the reabsorption.
Right, and when it comes down to it, the reabsorption, even though we saw some details, again, it's almost really, when it comes down to any kind of test question and all that, it really is just remembering exactly what I said. Because, again, this is where the detail is going to go crazy on the kidney. So for that, it's simply, most of the water, bulk reabsorption, proximal tubule. All the glucose, all the amino acids, most of the water, most of the salt. That's literally that. Okay? Boom. So the hard part of this was sort of the GFR. The 3 forces and the 2 local controls. Okay, so see, I mean, the trouble with it is that it's after all this other stuff. But I mean, in and itself isn't that bad when you go back over it. You'll see what questions. You just go over the, the three forces of filtration and the two local controls, and then the proximal tubules is literally just say that 5 more times and you've got it. Okay, that's it. There's nothing else beyond that. I'm not going to put secondary active transport and all that. You just have to remember what I just said. Okay, so yeah, that's why chapter 19 is like a tease. Okay. That's why just know those things. Just practice the three forces and practice the two controls and say proximal tubule, da 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 da, and boom. That's all that's really all in the chapter.
So we can forget about the neural.
Forget about that. Anything else I didn't talk about really that's in the notes you're not going to need to know. Okay? Because anything of that we're actually going to cover in chapter 20 anyway that I care about. So really, that's literally it.
What did you ask about the fetal?
There's other things if you look at the notes. I forgot which one did you just say? Oh, there's systemic controls of GFR that I have like in a page that you just don't have to know. That's why I skipped it. And there's other stuff in there too that you don't have to know. But anything else that I didn't say that's in that handout right now, I'm actually cutting out material that you don't simply need to know. Because really, this is all I care about chapter 19. So all the other stuff, don't even worry about. Literally, just we introduce sort of the parts, but really it's sort of filtration. What got in, and how we controlled it, and we got it mostly back in the proximal tubule. I should have just said that. But there's a little detail there. But that's all you need to know for chapter 19. So we stayed an hour on stuff to do, but that's really it.
I was writing the middle of that part. So can you repeat that one more time?
Sure.
Filtration.
I mean, wait, let me write it down. If I,
That would be awesome.
That would be awesome.
well, let me make sure I'm not saying anything wrong here. Let's go to chapter 19. I don't want to be there in chapter 19. Okay, so factoids we'll find out. Okay, blah, 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 blah. I mean, you have to look over a couple factoids there, right? Cortical versus junction measuring. I mean, that's just a factoid. And in knowing the names of everything, but I think that won't be hard.
It's like the anatomy, a little bit of the anatomy.
You what?
Okay, a little bit of the anatomy.
Well, except we're going to keep using these names so much, it's almost, you'll find out it won't be important. But you got to know the names of the tubular elements and the name of the blood supply. But, yeah. I mean, these are the 4 things, but that doesn't matter too much. So, yeah, it's filtration. As far as, besides those little factoids, which aren't much, it's basically, filtration. Again, sort of, how it works, which is shown here, just being size and charge. How it works, what doesn't get in, what gets in, what doesn't. So, what filters into the nephron, and of course, correspondingly, what doesn't. And all you have to think about is what doesn't. What doesn't make it in?
Cells and
Cells and protein.
Oh,
Good, we've got that. Cells and proteins. Okay? Then, so we have that. Again, that's pretty easy. Then the hard part probably is, those are pictures. This. Well, I mean, the harder of most of it is remembering, here are the 3 pressures that contribute to GFR. And remember the liver failure, how to play with it. So you have to basically know that and sort of the 3 pressures involved in, what's going to control the rate involved in GFR, and the 2 local controls for GFR, which were the myogenic response and that JG response. Where is this? This guy. The JG response. Okay, we can make a simplified picture from that. Just remember too, the macula densa, because usually I have some sort of question on that, because I want people to remember the macula densa are actually, sensors for salt, osmoreceptors that are part of this ascending loop. So don't think of them as, part of the veins or anything like that. They are literally cells of the ascending limb. that are going to then send signals to these granular cells, which we'll talk again in chapter 20, which are surrounding the vessels, and they're going to signal the arterioles to constrict. So again, so really it's not that bad when you repeat it, right? That's what you need to know, and then for the proximal tubule, blah, 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 bulk reabsorption. So, that's it. That's really chapter 19. So this is probably easier than Alveolar. But remember I said 17, 18, 19, 20. 18 was the hardest of the respiratory, 20 will be the hardest of this.
Would be one.
The JG response. It's not going to be any kind of essay question. I'm going to tell you the major essay question in chapter 20 next time when we talk. So you just have to kind of basically understand the process here.
There was a few slides before this one that did not have anything on the printout, but you did on the
Yeah.
this.
Oh.
I didn't get a chance to write that down.
Well, you have the PowerPoint though. I mean, it's
Right,
not on the
it
PowerPoint?
wasn't on the
No.
PowerPoint.
Where?
It was right before that one, I think.
Well, show me. So it's
It's like before these, but after this.
so. This one?
It was the one that looked like this, but it had a bunch of writing to the right side of it. I didn't get a chance to.
Well,
Some of it's further on.
well, I mean, that's.
This is before the neural and hormonal.
Do we have to know the equation of the amount that equals the amount of solid excrete?
Probably not. Let me see which we're referring to.
Yeah, not filtering away the
Well, you can kind of.
Well, it makes sense.
Yeah, it makes sense.
Are we gonna do any calculations?
I don't know. Maybe. I
Just
mean-
say no.
There's calculations on there, but it might not be that one.
Pulmonaries? Oh, sorry.
Well, I'm not sure what,
Okay, well, never mind then. I guess we have all the information now.
yeah, if you wrote it, as long as you wrote it down, because I can't be sure.
Okay.
For the test, are you having like pulmonary questions like you have on this lab test about like,
Exactly. That's why the lab test, the blood type problems won't be repeated, but a few of those, of the other ones, especially, of course, I'm going to have, because the big one that I care about overall, I'll have a Boyle's Law one on, because that's easy, P1, V1, P2, V2, and I'll have definitely a obstructive versus restrictive problem, right, where you have FEV and the total, but I'll give you that, because that's restrictive versus obstructive. I'll see if I have any more, but I'll definitely have those two on. So. And I'll probably have an alveolar versus pulmonary ventilation. So those, I'm probably not going to put one of those Dalton's one when you do the atmospheric thing. I'm not going to do that. But probably at least one of those others. I mean, one of each of the others. So again, that's while you're looking at that. Again, you have all the problems with that. So it's going to be whether I have all three. I'll see pulmonary versus alveolar ventilation. I'll have a P1, V1, that's an easy one. P2, V2. I'll definitely have that. And I'll definitely have, so whether I have pulmonary versus alveolar, I don't know, but do it. But I'll have a P1, V1, P2, V2 because it's easy, relatively. The harder one, which I will have though, will be that FEV type 1, where you have the FEV percentage and you have the relative vital capacity. And you've got to tell me restrictive versus obstructive, okay? The stuff we did in lab. And those are the problems with that. I'll definitely have that, and I'll have a P1, V1, P2, V2. I might have that the pulmonary versus alveolar. I won't have a Dalton's Law, 760 atmospheric pressure, and it's 21%. I'm not going to do that on there. But know those.
one has to do with your inhalation and the other one is the expiration.
Yeah.
So with the forced expiration volume, would not only be the obstructive one?
Having a below normal FEV1 is the obstructive one. having below normal vital capacity compared to normal means you can't inhale it, and that's a restrictive one. And again, if you don't have that overall, the two equations again were the idea that we were going to have measured VC, which is vital capacity, over predicted VC. I'll obviously give you this in different values. Over predicted VC times 100. That's saying, how much of what we predict can you actually inhale, basically, measured VC. And the other one is this idea of your FEV 1.0, how much forced expiratory volume, how much you got in 1 second over, really important, your measured VC times 100. Because again, overall, we have this idea of here's our tidal volume, here's our vital capacity, how much we can move through our lungs. We'll inhale as much as we can, and exhale it all. That's our vital capacity. And so, if you have, and again, we can just quickly write up the two. We have restrictive versus obstructive. Lung disease, rest versus OBS right now. But we're looking at these two things. What is our VC compared to normal? And what is our forced expiratory volume percentage compared to normal? Let's just write that again. So for restrictive, we are restricting inspiration. Okay, I'm just going to sort of not write it all out again because we have this. For obstructive, we are obstructing expiration. So for restrictive, we're talking lung fibrosis. We're talking neuromuscular, where you can't do your diaphragm. Actually, where is she? We had pregnancy. Who's in the lab with that? It was so cool.
Yeah.
So obesity and pregnancy, I guess they wouldn't call it diseases, but they could cause restrictive problems because you can't expand your lungs as much. So that was sort of cool. But really, we're talking, again, like we write, fibrosis, neuromuscular. As far as obstructing expiration, talking what? Asthma, COPD, emphysema. Good example.
I thought emphysema affected the alveoli, like they were like blown out.
Yeah, well, this is interesting. Emphysema is an obstructive, but the reason it's obstructive isn't quite like it's shown there. It's that your alveoli have lost their elasticity. And so what the idea of that is, remember, inspiration is based upon the idea of your diaphragm went in and basically, so it's going to expand. So it's not a problem with you being restricted, right? You expand. But instead of having, it's almost like we've done before, instead of having a balloon when we did vessels, which, usually you have elasticity and they'll come back, the idea is it's like a plastic bag. So you lost elasticity, so it's like, now you want the air to go out, but it's not gonna respond back. So because of that, it is considered obstructive. But you're right, it's completely different than like a blockage. It is the fact that, you've lost the elasticity in your alveoli. Okay, so again, to put it this way, again, overall, if you look at restrictive, okay, which one is that going to affect more? If you're restrictive, can you inhale as much? Is your vital capacity is great? That's why. So you're only going to basically get a lower than normal number one. I got a little yellow up. You have a lower than normal vital capacity. Your measured vital capacity is below normal compared to your predicted. So you'll have that. However, in general, because this is in general, if we say, okay, that's how you get in, you don't have any obstruction. So we say blow whatever that is out as fast as you can, and you're like, no problem. So you have a normal, and remember, we're in ideal conditions here. So a normal FEV. For obstructive, if we say inhale, take your time, but inhale as much as you can, is there any problem with expansion here? So you have a normal vital capacity, but in this case, or even the emphysema case, if we say, so we're okay up there, we say blow that as fast as you can, are you going to be able to get it out as fast? No. Okay? Maybe it won't be that bad. But you're not going to be able to blow it out as fast, and so how much you get out in 1 second, which is the second equation, how much of that measured vital capacity, don't put predicted. That's the common mistake, right? The FEV over the measured, because we're measuring, actually, we're figuring out whatever you did here in lab or in the test, how much did you get out of that first second? That's going to be below normal. And those will be your two choices. okay? I'm not gonna give you, well, I might give you on a test question both, or you know, I mean, when I do my multiple choice thing, but I'm telling you, don't put both, because I'm not going to give you both, okay? So, it's either gonna be one or the other. And my choice will be normal too, but I'm not gonna give you normal, I'm gonna give you one or the other, okay? So, that's that.
Which one did you say you might give us both?
No, I'm not, I mean, for A, B, C, D, I'm gonna put those
for the
in.
choices,
I'm gonna
yeah.
give the choices, but I'm telling you, I'm not gonna give you one of those choices. You can eliminate those right away if you're here. It's either gonna be a restrictive or an obstructive, you know. And again, I could use those names, so don't forget the names. I could just say, you know, it's COPD or it's asthma. So I won't give you anything else I didn't talk about here, but I probably won't give you pregnancy.
You cut off 70 for both, right?
Yeah, and I'll literally tell you. And I'll tell you, and I'll say on the test too what percentage I want, and I'm actually gonna give 70. If I do pulmonary alveolar, remember that's talking about dead space, I'll give you, it will be 150, but I'll give you dead space as well.
Dead space.
Yeah, what are you talking about?
What are we talking about dead space? Are we in Halloween? Let's see. Let's go back. Don't talk this dead space stuff.
Deathly Hollows.
Okay, so we can do one of those. Oh, that makes me feel better already. Okay. Okay. All right. So let's look at the dead space problem. This is how we breathe. Here we go. And I don't like that figure, but we're going to use it for this. So the idea of this is, and this is how to do these problems, and I'll rewrite this. This is why we're here, you 10 people, to extensive review. You can find out where I live. You can knock on my door, and I'll be like, okay, I'll go outside. I'll talk to Kidney. Okay. I got to show you this. There's only a few people. Let's see if I have this here. Hang on. It's so cool. Okay, so I'm teaching, and I actually next semester I have it too. At San Marcos, I teach different classes, whatever they give me. I'm like a dog, they're throwing bones out here. And this semester, I'm teaching physiology for non-majors. You have to take things outside your major, and you're like, oh my God, it's 7:30 in the morning yet, right? I'm like, no one's going to show up as a non-major for human physiology. So it's human physiology for non-majors. And guess what I just taught them? The kidney, okay? And I actually taught them the cardiovascular, and for their question, I said, like what you did up there, I'm like, this is going to be the essay question. I didn't put all the details in. And so we were worth like 25 points, because remember, this is non-majors. And almost all of them got all this, and I'm like, oh, this is so cool, they know this. So for the kidney, I talked a lot about things, including the nephron and stuff, and talked about it. And I also talked about alcohol being an ADH inhibitor, and the idea of salt attracting water and all that. And so everyone got all these right, because I told them I was giving the test. But this one girl, basically, when talking about it, actually drew me in a margarita and drew little like NA pluses around for salt and stuff. And I was like, this is so, I was like crying about it. This was like so, I mean, I'm very emotional on the kidney stuff, right? And so when students do stuff like this, I just like, it's so cool. It's like 60 people. These are like finance majors and all that. Almost everyone got that right. And they kept going on this. Well, we crave salt because we need water, and salt, water follows the party. Water follows the party. I'm like, this is so cool. I'm sorry. But this was really, really cool. And these are non-majors. And again, as a teacher, I'm trying to make impact to everybody on certain subjects. And I'm like, I didn't know how to do this, right? This is the first semester, like, how much is too much and all that? I'm still not sure. I'll find out when they rate me, But I do, the thing what you'd be jealous are, my tests are a lot easier. They're not nurses, all right? So, but you have some of the same information that I'm giving you. I'm just saying I counted for more, and I don't put as many tricky questions on, so, or whatever you want to call it. Anyway, sorry. I diverged, but it's so cute, right? I got to keep that one.
Oh, wait, whatever you're erasing right now, I wrote it down, it's fine. For the bronchioles, so their job is to deliver oxygen to the alveoli as needed. So under conditions of low O2, they're going to vasoconstrict, right? Dilate?
They're going to bronchio. You're talking about bronchios, right?
Yes.
They're going to bronchiodilate you. If you want to deliver, I don't know what your delivery schedule is. If we're delivering, I want to get more, okay? So anytime you're delivering, you're opening up. Okay? If you're, basically, yes. And if you're picking up, you're going to where it is. Are we doing this, or are we got another question?
I have a different question once we're done with this.
Okay, let's just do this. Okay, so, because we got,
That's right, I'm sorry, I forgot.
I know, we forgot about dead space, and I'm almost out of chunk. Dead space. Okay, here's the idea. We're back in chapter 17. we're back in Kansas now. Remember how 17 was nice and we're breathing? Okay, so for 17, we're talking ventilation. How much air we're moving in and out of our body. And, there is a concept, there are two terms here. When we talk total pulmonary ventilation, we're just saying how much we're moving in and out of respiratory tract. Okay, I'm not going to try not to hyperventilate. Now, when I inhaled, let's say I inhaled 500 mils, my tidal volume, did all of that reach my alveoli for gas exchange? No. So the amount, and I hate this figure here, but it has it up here. The amount, let's say you inhale 500 mils, the amount of air that doesn't reach the alveoli, that's still in my mouth and my trachea and my, my bronchi, that aren't doing the gas exchange, that's called dead space. It seems drastic to call it dead space, but the bottom line is that's not reaching for gas exchange, and we sort of care how much oxygen we're getting in and CO2 out. And that's called alveolar ventilation, how much actually reaches the alveoli. And so the difference is, and again, I'll give you that number. Obviously, it's different for each people, right? Each person, they're different sizes, but it's around 150 mils. And I'll give you that again. So this thing is like, God, I can't even deal with that. I should just put another picture up, someone breathing or something, because that just is crazy. But so here's how to do those problems. If you haven't had it before, we can kind of look at it. I'm using this as an example. I don't like the way they sort of put it up here. You have to calculate, again, pulmonary. It could be total, I guess a little bit total. Pulmonary ventilation. Again, that's how much air per time, how much air per minute you're moving in and out. And that's going to be what? It's going to be tidal volume. That's kind of, the basic breath you're having. Tidal volume, okay, which is mils per breath, times breaths per minute. Okay, again, that will equal then, mils per minute, or liters, depending on how much we get to. That's how much air in a minute we're moving in and out of our respiratory tract. Okay, and again, if we sort of put the numbers there that they sort of have, we'll just look at the top one. If our tidal volume is 500, okay, and I don't feel like even putting the units here, but 500 mils per breath times 12 breaths per minute, it equals 6,000, I'll go ahead and put it now, mils per minute. How many liters per minute is that?
Is it 12? No.
How many liters is 6,000 mils? If you convert that to liters, how many liters? 6. Okay? You want to get familiar, as far as the metric system goes, get familiar with that one. You can forget deci for a while, but you want to realize there's 1,000 mils in a liter, you divide by 1,000. 6,000, 6 liters. I actually put it. It's not going to probably matter for a test right now, but I just since you're here, I really care. That's the one you'll use the most. All right? Anyway, that's your total pulmonary ventilation. But we want to also know how much actually reached the alveoli. That's the alveolar ventilation. And to do that kind of with this formula is, you're going to do kind of the same thing, but in parentheses, we're going to have tidal volume. Let me just say TV. You can write out tidal volume minus dead space. End of parentheses. Because this is going to be for each breath times breaths per minute. Sounds like beats per minute, but it's breaths per minute. So, for that same example, which is what they're showing up there, that means you're going to have 500 minus dead space, which is 150. That means you have 350 times 12 breaths per minute, which is, 4,200 mils per breath. So those are the two calculations, and then I'll just mention this up here again, sort of why they did these other things down here. So those are the two calculations you need to know. You're given 3 things. You're given the tidal volume, you're given the ventilation rate, and I'm giving you dead space. So
Mils per minute, or liters?
mils per minute. Thanks.
What's your number again? I'm sorry.
What?
It's 42.
4,200.
Okay.
So, I mean, they're doing the same thing, but, you know, they're doing it in this method versus my method here, right? They have tidal volume minus dead space, is 350 times the 12. Okay, so they have it in this dyslexic way, unless you like the table. That's how to do it, though. You're given tidal volume, you're given ventilation rate, and I give you dead space. To figure out pulmonary ventilation, you simply multiply tidal volume times breath per minutes. Okay, because that's just how much air you're moving in and out. If we want to know how much reaches your alveoli, we've got to subtract dead space from each breath. And so in this case, it was 500, and dead space is 150. That means each breath, only 350 is actually reaching your alveoli. And we care about that for gas exchange. That's why what they show in the next examples are, let's say you want, you know, more gas exchange. You're working out, you need better oxygen and CO2 out. Is it better, you know, kind of, you know, theory here, is it better to breathe deeper and slower or more rapid and shallow? You know, and we kind of knew that anyway, but this is kind of showing it sort of mathematically. So they gave an example in which they could, you know, a couple examples of rapid shallow versus deep slow, in which when you add it, when you multiply it out, they end up having the same total pulmonary ventilation to sort of make a point, okay? But you can kind of, again, it's going to make sense. If you breathe rapidly and shallow, out of that 300, half of it's not even making it. So when you calculate your alveolar ventilation, it's actually down to 3,000. You know, you're just hyperventilating, you're going to probably pass out. Now, if you go the other way and keep that, where you're doing, you know, very deep and slower breaths, they equal the same total pulmonary ventilation. Look what you did for the alveolar, because now, out of that 750, 600 of each breath is making it in, because dead space is only 150. So they're sort of making a point that in general it's better to, which we kind of knew anyway, right? It made sense. And it's better to have a more steady, deeper breath than it is to sort of have that shallow breath. But now we sort of have that, now we know what dead space is. Dead space.
The top equation is the total pulmonary
Yes.
ventilation. What's the bottom called?
It's not called anything. It's called the alveolar ventilation, right? It's basically how to calculate alveolar ventilation. It's kind of the same, except for each breath, tidal volume minus the dead space. You're going to subtract 150 from whatever that tidal volume is for each breath. That's why it's in parentheses, or the way I did it. I mean, they do it too. They just have it in tablet form, right? They do it that way.
And so that's how we know how much air reached the alveoli.
Right.
For gas exchange.
Exactly.
And what would we need that for? To apply to where?
To apply for, are we getting enough gas exchange, okay? You know, because, you know, if a person's becoming hypoxic, okay, or if you're exercising, you need more, you want to know sort of, you know, you sort of use those values. Yeah.
I was gonna ask about that, if you exercise more, maybe it's a couple questions, but what were you talking about, athletes in their body, they have less oxygen or something? I don't know.
Use it for
I don't know which thing we're doing. So,
Well, that's why I don't know, I'm kind of confused about both, like, what happened, what did you just say about hypoxic versus exercises excessively?
you don't never.
Never mind.
If you think of it, I don't remember which one we're talking about. I don't even know what chapter we're talking about. I mean, right now from that. That's right. We just did 3 chapters. Now, which one were we doing? The saturation curve? Were we doing this?
No, I thought there was a specific point just in one of them that was talking about.
Gas exchange, the hypoxia,
Yeah.
hyperemia. Well, I had like a similar question. I wanted to go through the gas exchange because you put like there's hypoxic, hypoxia, anemic hypoxia, and if there was something wrong, let's say if you, now would that be like your anemic hypoxia? So that's something wrong with specifically the hemoglobin.
Right.
Now, how would hypercapnia work into that? Is that something? I mean, that's not elevated blood CO2, but does that correspond with hypoxia? Like if you have hypoxia,
Not necessarily.
is there an example you have of hypercapnia, like in the?
Well, I mean, decreased respiration. You know, so if you have, I don't know what to call it. Say again?
High CO2.
Well, no, we're saying what can cause it, right? So if you hypoventilate, okay, and we go back there, we can draw the equation. If you hypoventilate, you're going to build up what? CO2, okay? Hypercapnia. Okay, and also acidosis. So, because again, really acidosis and hypercapnia are really tied hand in hand now. Do we sort of see that? High CO2 becomes acid, and so that's really the key. So again, that's one way to do it, and we'll show you kidney problems as well. But hypoventilation, you build up CO2. Okay, so yeah, a decreased ventilation rate will be associated with it. So decreased ventilation can cause both, right? Decreased ventilation, you could cause hypoxia, okay, and potentially could cause hypercapnia. It just depends on the condition. It doesn't necessarily cause it. If you have the last one, toxic hypoxia, which is when you're poisoning the cell, that might not limit your ability to get rid of CO2. It's going to limit your ability to use oxygen. If you go back to that last one.
Which one's associated with divers when they don't, just as a curiosity, like if they don't relieve, like they don't blow the bubbles out as they
That's
go
for
up?
nitrogen, right?
I don't know.
The bins.
Yeah, that's what nitrogen. But yeah, I have to look that up too. I don't. It's like there's a whole chapter in this other book about basically deep sea diving and how that affects gas exchange, and I don't know it. I can't
It's like
pretend
my
it's a
when
question.
he was going through school, one of the guys didn't do that, and he blew out his eardrums.
Whoa.
So he didn't know. Like literally, it came up and his ears were like bleeding.
Oh. Yeah, that makes me not want to do that. That's like drowning big time to me. That's like I want to drown deep in the ocean. I don't even just want to drown in the snow. Yeah.
I have a question about O2 transport. We had the 6 steps. The first 3 were just transporting, and the last 2 were unloading. The last 3 confused me. We have O2 diffusing from the plasma to the tissue. Then we have O2 diffusing from the red blood cells to the plasma. How does that? I thought it was in the tissue. Why did it leave the plasma to go back into the plasma?
No, it did.
Or
Wait,
maybe
which
I
one?
wrote that down.
It
This
was
is-
it was that weird picture, you know, that you were saying that you did this step and then this step and this step, but the picture was showing different.
Well, it doesn't show it differently. It just doesn't show it very well. But wait, I don't want 13. Wait, do I? No, 18. This is 18. Okay, let me do it and show this picture and show what we're talking.
I think you need to rewrite it in a way that makes more sense.
Well, okay. So yeah, well we can use this over. So the first 3. I mean, again, and don't even freak out on it. I just don't care anymore. I mean, because it just. In other words, these first 3 make sense, right? Diffusion, volume, hemoglobin. Okay, and let's call it a day, basically. That's what we want to do. But when we go to the other side, obviously we know hemoglobin. Now we actually know quantitatively hemoglobin is going to end up releasing oxygen. It's going to go to the tissue, right? Now, and that's all I care about. But the part of me that's anal on this cares about how we're doing this. The idea is we're not going to have hemoglobin doesn't just go to the tissue because we say we would like you to do that, right? It has to do again with concentration gradients. And so the first step is that remember we did this diffusion. Everything was at equilibrium, right? We had from up here we had the right amount of oxygen out compared to the right amount of free oxygen in, and we reached equilibrium. Right? This was the whole idea. We did this, and now this was constant, right? The amount of oxygen here equilibrated to here, equilibrated to here. After we settled down, right?
It's when
Yeah. Okay. Right. And actually, it's all like 100. If we even go back just a second to even a simpler picture, which is this one I'm trying to get to. The idea is once we do all that. Just look at numbers here. We start out at 40, didn't have much. Here was 100 in the alveoli. So after we do all those 3 steps, everything's at 100. Okay? That's because that's what equilibrium is, right? But when we come down here, okay, we're at an imbalance, right? And so that's when we're going to unload it. So let's go back to this picture. So the thing is, people want to go this. They want to go. The hemoglobin's going to release it. And then it's, this is plasma here. It's going to go to the plasma and then the tissue, which it is. Okay, that's what's happening. All I'm saying is that the physics of it really are that it doesn't know to do this. The reason it's going to do this is that the first step is there's a higher concentration of oxygen. They're not fused here, right? The blood cell's not fused. We have plasma here next to the tissue. There is basically more oxygen here than here. Yes. So which way is oxygen going to go? Okay. This was an equilibrium, right? The free oxygen here and the free oxygen here. By doing this, what have we recreated here?
Concentration gradient.
And so O2 is going to now go
Into the plasma.
onto the plasma. Now, if we do that, what's going to happen? By a couple ways. By law of mass action, if we do this, it drives this. Also, if there's less oxygen, the hemoglobin saturation curve says less is going to be there. So it's this driving this, and so it's kind of the opposite, right, that we did up there. So you know why? That's why I did this is 4. That caused 5, and therefore 6. But don't. I mean, it's not going to be like a essay question. You got to put them in the wrong order because you can see I just don't care about it as much. But you see what I'm saying, right?
Yeah,
that
absolutely.
that this is what's happening. This is diffusion. Okay, it's not like we've got a motor and we say go. It's like the only way this is going to go is if yeah.
Yeah.
So it's this, and now we recreate a concentration gradient. So this flows out, and now we've got an imbalance here, and that will help it unload. So it is da 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 da, but it's da da da. So, but don't worry about it.
I have it here. I just, this little guy, I had the same concern, but
Oh, okay.
right here. See, that's 4 and 5.
If we're doing the reverse for that,